It's on? Okay, perfect. Okay, good morning. Just waiting for the slides. So I'm Federico Ronchetti. I work at CERN. I will not discuss my work here. I will just try to give you some basic facts so that you can maybe decode all these discussions in a better way. But before I start, I just would like to thank the organizer for this opportunity to speak. Then I would like to just catch up what Stefano mentioned about communication. So in this talk, my point is not to give you sterile notions, but just to enable you to better communicate with us scientists and all together, because we need to get rid of a lot of ideology and a lot of miscommunication that happened in the past. So let's first discuss atoms and nuclei. There are two different things. Nuclei are much smaller. Basically, an atom, the simplest atom is hydrogen, has a positive charge at the center of it, and then there's some negative charge, the electron spinning around. We have more complex atoms, carbon, oxygen, nitrogen. Then we have the nuclei. The nuclei, it's the core of the atom is much smaller. And so there's not such thing like atomic energy. Atomic energy is chemical energy, fundamentally. Nuclear energy is the energy that comes by doing something to the nucleus. Atomic energy, in principle, is a chemical reaction. Then there is something also inside the nucleus, but I will not discuss this today. Let's check a bit the concept. So if an oxygen atom would be as big as a tennis ball, a red blood cell of our blood would be as big as Manhattan. Okay? And the nucleus, so not the atom, the nucleus, so this stuff that it's at the core of the atom will be a sort of sand grain sitting in one of these offices here. So this gives you the scale, and you can understand why nuclear energy is so powerful, because it's energy that is densely packed. But what is energy? We are always saying this word, but do we really understand what we mean? So energy is the capacity of a physical entity to perform some work. And then what is work? Work is the displacement of a force. So what Sisyphus does, it pushes this big rock up, and what it does, it works against gravity. It moves the point of application of this force from here to here. And then the thing falls down, and the energy that it gained when the rock is here, that's potential energy. And when it releases the rock falls down, it becomes kinetic energy, and then it starts it over and over. But something happened. Heat was produced. So this process is not reversible. There is a loss here. So energy can take many forms. I showed you here some of them. Kinetic, potential, I mentioned. Nuclear. Ionization also is a very important form of energy, where we strip off electrons from atoms. And heat. Heat is also energy, but it's energy with the degraded capacity. It's like having a currency that doesn't have any pouvoir d'achat, any economic value, like, I don't know, very poor country currency. So this is the concept of entropy, which is also very important. Then, sorry, I went too fast. So there was the nice introduction about fusion and fission. So how do we get energy out of the nuclei? By fusing them or by breaking them. In the end, what happens is that we have released stuff, and the difference of the energy from the initial state and the final state is the binding energy of the system. And this is very high in the case of nuclei. So you see here, this is how the nuclei is heavy on the horizontal line. So you see this curve. If you fuse elements, it means you go from light elements to a bit heavier elements. You get this advantage of released energy. If you break elements, you go from, say, uranium to smaller byproducts, then you get this amount. So you see the amount from fusion is much higher than the amount of fission, but still the amount of fission is enormous. I remind you that the bomb that was dropped on Hiroshima was 15 kilos of uranium. So the energy release from nuclear reaction is basically a direct consequence of the relativity, as it was said in the previous talk. So it's basically mass that is converted to energy. And that's why it's much larger than the chemical reactions, so million of times higher. What is this energy in the end? It's just kinetic energy, so speed of the particles that are produced. And this speed becomes heat. It's released as heat. And heat then can be used to make water boil and to run a turbine. So is it dangerous? Depends. Is it chemical energy dangerous? If you fuel your car, I don't think you feel unsafe. You refuel your tank and you go. If you throw a light match in a tank of gasoline, then you may feel unsafe. So it depends, as Stefano was saying, it depends how we use it. The same is for nuclear. We can use it for civil purposes to produce carbon-free energy, or we can make a bomb. It's up to us. Then I want to give you a few concepts about radiation, because also here I think it's very complex and there's a lot of confusion. First of all, I want to say that radiation can be thought as energy that travels from a source to a target. We have very many kind of radiation. Electromagnetic energy, light, is radiation, and it's propagated via electromagnetic waves. This can be ionizing or non-ionizing. What does it mean? It means it can break atoms or not. If it breaks atoms, then it's dangerous, because it can break also the atoms that make the molecules and the biological molecules, and you can have biological damage. It does not happen always. If you use your cell phone, that's not ionizing radiation. This light is not ionizing, but it can release heat still. Anyway, it will not damage your cells. And then we have radiation in forms of particles, usually are this kind of particles. I will discuss them a bit later. And these are all ionizing, so they do break atoms. Basically, these different kind of radiations can induce biological damage. They can be shielded with different techniques. In general, neutrons and gamma rays, which are a very high frequency form of light, are quite dangerous because they are neutral. They don't carry electric charge. So they do break nuclei, and they pass through materials in depth. While these other forms of radiation, they can be stopped quite easily. Another thing that I would like to mention is don't confuse radiation in general with contamination. Contamination means that we have radiation in an unwanted place. So if we fire an atomic bomb or a nuclear bomb, then of course you contaminate. Chernobyl is an example of contamination. If we run a nuclear power plant, we manage the process. So there's no, let's say, contamination in the strict sense. Then let's discuss a bit what means biological damage from radiation. I want to go into this because I want to show you that radiation is a risk as any other thing in life. There's no such thing like risk-free activity. I can sleep now and break my ankle, or anything can happen to anybody. You smoke, some of you smoke, so that's risk. Basically, if we have a radioactive source, we can define the activity of the source as the number of particles that the source shoots at any second. So it's like a machine gun is firing bullets, and this is the activity. The dose is the energy absorbed by the target. So the target receives these bullets and absorbs them, and this energy released. And the effective dose is the damage. So the damage is different. So here, these radiations, they have different effective, different biological damage.
These alpha rays are harmless if they are outside the body. They can be very dangerous if they are inside, for instance, while those are quite dangerous always. So radiations have different capability to do biological harm. But this harm is, I will show you, is comparable to risks that we take every day. So how do we handle this? First of all, let's understand one thing. Radiation also occurs naturally. So we have radiation from cosmic rays because we have supernova exploding in the galaxy that send very high energy particles up to the Earth's surface and also beyond. We have radiation coming from the soil. We have radiation coming from natural isotopes that we eat in foods like bananas or Brazilian nuts or many other foods. Then all this amounts to a background that we absorb every year. So every person everywhere, without doing anything, just living, absorbs this. Our body is quite well equipped to deal with this. Our cells can self-repair. They are quite capable of absorbing low doses of, let's say, chronic exposure. If you have strong doses of, prompt exposure, then it's another thing. But as we said, we don't want to make bombs here. We want to make good use of this energy. This is a map of the exposure to cosmic rays in Europe. So clearly, if you live on the top of a mountain, you get more radiation. No power plants, no bombs, just from space. If you are on a flatland, then it's less because you have more atmosphere absorbing this rays. And as I said, from food, some calcium carbonium isotopes are radioactive. This carbon-14, it's an isotope that it's mixed with the normal carbon atoms that we have in the metabolism, and it's radioactive. And when we die, this intake stops, and then it starts to decay, and that's why it's used to make carbon-14 dating. And potassium-40 is the same. It's in some foods, and we absorb it, and then it emits gamma rays. Then finally, I come to the concept of risk. So I try to show you that any human activity is potentially dangerous. And we have this concept of risk, which we understand in an intuitive way, but I would like to make it a bit quantitative. So what's a risk? A risk is a danger, probability of a danger that you multiply for the probability of a failure. So imagine a tiger. If you go to the zoo, the tiger is behind the cage. So the tiger is dangerous, so the risk is 100%. But if you put the cage in front of her, then I would estimate that the chance that the cage breaks or something happens, it's 1 over 100,000, then the risk is 0.001%. If you go for a safari and you start walking around by yourself, then maybe the risk is 100%. So risk 0 does not exist. It depends always from the policy you implement. And I think we need to have an approach that is rational to risks and also to the risk connected to nuclear energy, which are, as it was also mentioned, can be made not different from everyday risks. I think I will stop here. The conclusion you can read from yourself.